All right. Today we're looking at Chapter 4, which deals with our elements, atoms, and ions. An element is our simplest form of matter that has chemical and physical properties. Right? What I mean by matter is it's just solid, liquid, or gas. And the unique physical and chemical properties are simply there because a element is the smallest thing that has a unique physical and chemical properties. There are things smaller than atoms, but they can't share both physical and chemical properties with the elements. Now, everything we come in contact is made out of these elements. They're just actually combined in various different forms. And we do not have the means to turn any element into another by chemical or physical means. So a carbon's always a carbon, hydrogen's always a hydrogen, etc., etc. All right. Our elements, there are 118 known, 90 which are found in nature, and I have, to go along with today's lecture, our periodic table that I have on Canvas for you. And this is showing our periodic table. So it has all 118 on here. There's 118 down there. This slightly thicker line is where these two rows would fit in. So technically the table could be wider and have these in, but most periodic tables just put a thicker line there and move those 28 elements down below. Now, when it talks about the, on our slide, it talked about the 90 found in nature. The ones that are not found in nature on the periodic table are actually hollowed out. They are just the outlines of the letters. And it really is everything from 93 on up, and then number 59 and number 43 right in the middle of the periodic table. And we'll be going back to the periodic table a bit. All right, so every symbol, every element has its name and a unique 1 or 2 letter symbol. First letter is capital, second letter is lowercase, but all of them have that, even down at the bottom. If you have an older periodic table, you might have 3-letter names for some of these down here in the 103 to 118. But since 2016, they've all had names, and that's what's on the periodic table is their accepted names. All right, on the next slide, we're going to see abundance in nature and also in mammals, human bodies. So oxygen is the most in all cases. Matter of fact, on the Earth, it makes up 49.2% of the mass of the planet. And the first 9, which is this first row, actually make up 98% of the mass of the Earth. And if we include all the first 18, you see how small fluorine is, and yet is the 18th most abundant element on the Earth. All the rest only take up 0.49% of the mass of the Earth. Now, our body's slightly different. We actually have hydrogen going to move up quite a bit. And that has a lot to do with the water that's in us, and every single compound in your body has hydrogens on it, and typically a lot of hydrogens. So our first 3 are actually oxygen, carbon, and hydrogen, and they make up significant more. And you can see all the ones you might recognize that have popped up in your diet and whatnot. One I always get a kick out of is over here, trace elements, is arsenic and chromium, which are definitely both toxins that you might be aware of. So it's kind of interesting. You have to have them in your body, but too much can be a bad thing. All right. The other just elements in general here. Biggest reason I left this up here is it does have some of the Latin names, which is where some of the 2-letter abbreviations came for some of the more common elements. Gold and silver on here, and you'll see that their symbols don't actually see gold. It's from their Latin counterparts, and it is simply because many of these elements were known in ancient times. Might not have known that it was a pure element, but they knew what the substance was and had isolated it. All right, the definition or the term atom actually comes all the way back from ancient Greece. This philosopher theorized that if you had a really, really, really sharp sword and kept cutting an object, you'd get to the point where you couldn't cut things anymore because there were atoms that were indivisible. Now, he didn't have any scientific background to actually prove this. This was just all thought. It's not like they had a sword back there that could do this. And he was around the time of Plato and Aristotle, and Plato thought he was useless and actually wanted all of his books burned on his death. Aristotle kept some support on there, but he's kind of the father of science because he actually predicted some, or he actually suggested some of the techniques and styles we use, but he's mostly known because he came up with what this definition of the atom is. Now, it wasn't until 1800s that an idea of what the atom actually is was described, and it was described by this guy here on the right, John Dalton, and he actually said the elements are made up of very small particles called atoms, and he did use that term because that's what the Greek philosopher called it, and he just said that the atom was the smallest particle of an element that retains the characteristics of that element. So if we're talking about a substance like gold, the atom would be the smallest part of that sample of gold that still is something you could consider gold. So divide it down into the smallest possible things. Now, his ideas were based on these 5 postulates, which we're going to look at right here. There's the other 2, but these are the first 3. So the first one, elements are composed of atoms. And he said these are tiny, hard, unbreakable spheres. All atoms of a given element are identical. And so all carbon atoms are exactly the same and have the exact same chemical and physical properties. Atoms of a given element are different from those of any other element. And again, we're talking about carbon. We'd say carbon atoms have different chemical and physical properties than any other atom. Continuing on, the next one, so the 4th postulate, atoms of one element combine with atoms of another element to form compounds. Now, he actually put in there this law of constant composition. It was built from previous scientist studies. He just expanded on it. But he actually said that all samples of a compound contain the same proportions by mass of the elemental formulas. What he's kind of saying is water, if that's the substance we're looking at, always has the exact same mass percent of hydrogen and oxygen, regardless of where we find it. And if we try to change that somehow, we simply can't. Now, it also had in there his law of constant composition also took an exception that there wasn't just one compound that would have hydrogen and oxygens. There could be more than one, but they'd have different ratios or different mass percents. But once you had it purified, it'd be the same. What I mean by that, there is water, but there's also hydrogen peroxide. And Dalton was showing and demonstrated that those 2 compounds would have totally different mass percents, and the mass percent of water would be fixed, the mass percent of the hydrogen peroxide would be fixed, and it wouldn't change from water molecule to water molecule. And our last one, atoms are indivisible in chemical processes. Now, he said at first they were indivisible, but he had to modify it as we discovered more and more things. And most of these postulates were modified in his lifetime to something that resembles today's idea. But now, when he says indivisible in a chemical process, he does say that if we react a chemical, we might change the makeup of the molecules, but the atoms themselves will remain unaffected. So if we were to take some gasoline and burn it, it mostly turns into carbon dioxide and water. Well, the carbon dioxide comes from the fact that there must have been carbon in the gas molecule, and the hydrogen does as well. Now, there might be some oxygen in there, but when we burn stuff, we know we need oxygen, so it's not necessarily required to be in the gas molecules. Now, I did leave it vague like that, because it turns out in your gas tank at any given moment, there's about 30 different components. Most of them are made out of just carbons and hydrogens, but we do know that there's other additives in there, and ethanol does have oxygen in it. And we know that about 10% of Florida's gas has ethanol in it. Okay, so what we're going to see is those compounds we're talking about are going to have chemical formulas. And they're just going to show whole number ratios of atoms. Now, there's never fractions. Water is definitely H2O. Hydrogen peroxide is definitely H2O2. And we would never see fractions. Like, technically, I could divide H2O and divide it in two and maybe say, well, that's HO1/2, because I'd still have the same ratio, but we don't ever do fractions in there. These are always going to be whole numbers. We're going to use the symbols from the periodic table to represent atoms, and we're going to use subscripts to represent the number. And just for some examples, C6H12O6 is actually the formula for glucose, which is most common carbohydrate in mammals. Actually, matter of fact, most of the carbohydrates in you right now that have been processed are glucose, about 80%. But it has a very fixed formula, 6 carbons, 12 hydrogens, 6 oxygens. All right, for instance, if I were just to say that, 6 carbons, 12 hydrogens, 6 oxygens, you can just flat out write it in the order I give it to you. There is no reason you can't put these in a different order if you want. Now, most of the time, we have a very specific set of rules. You'll typically find that carbons and hydrogens get listed first when you're dealing with the nonmetals, but it's not that critical on the order. All right, today's atomic theory has developed a lot since Dalton. It helps us understand what the heck's going on in the scale smaller than the atom. But heck, we're able to manipulate a lot. I love the idea that this picture here on the right, that does look like it's just a computer graphics thing, it's actually not. It's actually a scanning tunneling electron microscope that was actually used to physically move xenon atoms and arrange them in that form of IBM. So that's a picture taken with an electron microscope that they use the electron microscope to move things around with. Now, they've advanced that. They're doing all types of silly things. They actually got little stick figures they've drawn and little stadiums. And that's the actual picture of what a scanning tunneling electron microscope looks like. So it does have an actual viewfinder, but that's really just to position things. As you can imagine, these images were done on computers. It was just analyzing the data coming off. All right, so on to what the atom itself actually looks like from Dalton's theory. He actually at first had this idea of what the atom looks like. So there was a big, huge sphere of positive goo with embedded electrons in there. Now, the electrons were embedded like that because at the start of his, when he proposed his postulates and his theory, the electrons were known to exist, and they have roughly 1/1000th the mass of a hydrogen atom, and they were found in anything. So they knew there was a bunch of electrons. Weren't quite sure yet how many were in a given atom. They knew it was a small number, but they knew they were tiny, tiny, tiny little things. All right, so they want to prove this is the makeup of the atom, that it's that goo with tiny little electrons. So they're going to use this weird thing called an alpha particle emitter. Now, alpha particles weigh, so if I said this was 1/1000th of a hydrogen atom, that was for the electrons, this is about 4 times the mass of a hydrogen atom. Now, what they're going to do is bombard a substance with those alpha particles to dislodge those electrons. They're thinking, back up to this picture, it's just going to fly in here, and since it is just a positive goo, most of the alpha particles are just going to go right on through, not deflected at all. Some of them might come through here and hit an electron, but since they weigh 4 times the amount of a hydrogen atom, and these are 1/1000th, these are expected to just go flying off the electrons themselves, and then this particle might ever so slightly get deflected. But for the most part, they're expecting 100% of the alpha particles just keep right on going through. Now, this sample in the middle, it is gold. Now, the reason they chose to use gold is, if you're not aware, gold foil is actually gold that's pretty much transparent. What goes on with gold? Gold is such a wonderful metal for malleability that you're able to get it super, super, super thin to the point where it's actually transparent, and yet it's still gold. And that's why they use this. This would be like a gold foil, about 3 or 4 atoms thick, and the alpha particles are just going to shoot right on through. So even though there's more than one atom, there's still so few space, or so little space, that we're going to maybe knock these electrons off, but the alpha particles are going to keep right on going. Well, turns out that's not what they saw. Turns out when these alpha particles hit this solid, some of them came right back bouncing away. At the time, this confused them because they were expecting to hit things that weighed 1/1000th the mass of a hydrogen atom, and these weighed 4 times the mass of a hydrogen atom. So it'd be like, you got little smart cars and you're in a tank. Well, obviously, you're going to expect the tank to go right on through. Well, what they missed is the nucleus of the atom has all the mass in it. Little tiny spot. So it's better to say these electrons are in this gel like this, but dead center of this is a very dense nucleus that has all the mass. That positive cloud is not a positive cloud. It's a single point of substance. And it turns out on gold, that particular substance has a mass of roughly 197. So 197 times the mass of a hydrogen atom. So this wasn't a semi-truck, or this wasn't a tank hitting a smart car. This was a tank hitting a mountain. A massive thing by comparison to it. So that's why it stopped, and that's why they bounced back. Well, thanks to Rutherford's experiment and others, we now know exactly how the electrons and protons and neutrons are in a nucleus. For instance, we have the electron cloud, which is that big, huge sphere, and the electrons float around in there, and dead center is the nucleus. And in the nucleus are your protons and your neutrons. Protons and neutrons have roughly the same mass. That's what they're showing right there. We actually cheat most of the time. Rather than say it in grams, we say they weigh 1 atomic mass unit and 1 atomic mass unit. Seems like a cheat way of doing it, and it kind of is, but we are talking about very, very small things. It'd take a lot of these to actually make any weight whatsoever. But that is the actual mass in grams of a proton and neutron. But 1 is fine. And then we have our electrons that are just floating around the outside, and that is that 0.0005, also AMUs, that relative mass. So it's kind of interesting. The space that the atom occupies is mostly empty space. Even on our heaviest atom on the periodic table, which is element 118, it would only have 118 electrons in that outer space. Yet all that mass of 294 is roughly dead in the middle of it. Okay, so Dalton's theories are now accepted. There are minor little exceptions. So we say all atoms of a given element are identical. It's not necessarily the same mass. The masses vary. For instance, with regard to carbon, for instance, there are carbons that have 6 protons and 6 neutrons. And there are carbons that have 6 protons and 7 neutrons. This occupies about 99% of the time. This is about 1% of the time. But they do vary in mass slightly. But the 6 protons and the fact that it's carbon gives it all its property, not those neutrons. Those neutrons don't affect its chemical identity. And the other modification, this first one, it says all elements are composed of atoms. Used to say this, and they actually made this unbreakable as a hard rule. We do know now that you can actually have elements turn into other elements through nuclear processes. So in chemical processes, you can't break them. And physical processes, you can't break them. But nuclear processes, you can. Okay, so the structure of the atom is actually found with protons, neutrons, and electrons. All the protons are actually found in the nucleus. All the neutrons are actually found in the nucleus. On a given atom, you can determine the number of protons by finding its atomic number. Now, on the periodic table, that is the number that's right above the 1 or 2 letter symbol. And there is a number from 1 up to 118. So every single one of those numbers are telling you the atomic number. It's also telling the number of protons in that particular atom. So that does say that every sulfur has 16 protons. All right. Now, this also talks about electrons, or tells us a lot about electrons. Typically, the number of electrons is the exact same as the number of protons, as long as the atom is neutral. All right. The mass number, right here, is not shown on the periodic table ever. But it is actually the product of the protons and neutrons added together. That is where I came up with carbon having an atomic number of 6 and a mass of 12. The mass of 12 is 6, tells us there's 6 neutrons, because 6 plus 6 is 12. There is also carbon 13s. And if the mass number is 13, then the amount of our neutrons must be 7. So that's how those vary. That's what when we call those things isotopes. But on the periodic table, I won't see the value 12 or 13. We do have a number that's similar to that. If you look right below carbon, it's got 12.0107. We're going to see that that's something slightly different than the mass number, but there is a reason it's close to these numbers. All right. Number of neutrons do vary in almost every single atom on the periodic table. Almost every atom has multiple isotopes. Isotope is simply an atom that has a different number of neutrons. They'll have the exact same number of protons and the exact same chemical properties, but the neutrons vary. And here's that carbon again, and I got the 99% of the time it's carbon 12 and 1% of the time it's carbon 13. And right now in you, because we are all living creatures who have been exposed to the environment, we have approximately 10 to the negative 11th percent of our carbon is carbon 14, which technically is radioactive, and it will break down on its own naturally and turn into another atom. But radioactive carbon is found in nature, just not a lot of it. It's a very small percentage. But all 3 of these carbons behave exactly the same, and your body can't tell them apart. So any carbohydrate could have any one of these ratios in there and still behave exactly like it's supposed to, or like any other glucose or carbohydrate. All right, so if I was going to ask a question like this, number of protons, electrons, and neutrons in chlorine 37, my first step would be I would want to find chlorine on the periodic table and get its atomic number. And chlorine is right over here, has an atomic number of 17. Now that 17 tells us the number of protons. I'm going to write it right here, and I can just mark that one out because there's no way it's that. So 17 is right. Now, we do know that the protons and electrons must be the same in a neutral atom, so I know that's also 17. And on this problem, that actually finished this up. We didn't have any other possibilities. But if I need to figure out the number of neutrons, I just take that mass number and I subtract the atomic number. And that's where the 20 came from. All right. The atomic mass, different than the mass number. The atomic mass is the average of all those naturally found isotopes. For carbon, since we found most of our carbon to be carbon 12, its atomic mass is almost 12 on the nose. So if I go to the periodic table, you'll see that the mass underneath, the number underneath the symbol, never ends in like a bunch of zeros. There are these down here in the man-made ones. They're just in brackets. And that's because those are good guesses what their masses are, or the masses of the most stable isotope. But all the rest have something that doesn't end in 0. And that's because everything else has a varied number of stable isotopes, and those found in nature average out to the value shown here. So it's almost like saying this is the average mass number, but it's not what we say it. We call it the atomic mass. And then we're really able to say that because we're never really going to deal with atoms individually. We always have to deal with them in huge amounts because they are so small that even in a gram, there's billions upon billions of atoms. Okay, next thing we're looking at is a weird thing about the periodic table, and it's periodic law. Now, it basically says that our arrangement is telling us certain things about the atoms. It's grouping them with similarities. What I mean by similarities, turns out everything in this last group here, group 18, has a very poor reactivity. They're typically found pure. We call them noble gases or inert gases because they don't react with anything. And another weird family, group 1 over here, if I take away the hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium are all metals. Hydrogen's not a metal, but those others are metals. And they have similar properties to most metals, but they are very reactive. Matter of fact, any sodium sample I happen to have in my chemistry lab looks like a snowball because it's actually oxidized the outside so rapidly. But probably the most dangerous thing, and you can see this on YouTube if you're ever interested. If you search for any one of these and just say putting it in water, you'll see that you wouldn't want to cook with a pot made out of any one of these because every single one of these metals reacts quite violently with water. And they get even more violent as you go down. Like if you were to somehow manage to get about 5 grams of this, so a very small amount, about the size of a penny, and threw it into some water, that Homeland Security would come knocking on your door. That's kind of like a hand grenade almost. That's a very violent explosion. Now you can get sodium. I mean, matter of fact, you can buy it off YouTube or off eBay if you wanted to, and throw it in your pond. The neighbor's going to call because it's going to make some ruckus. Might want to look at that on YouTube before you decide to actually buy it. But what we see, what I was summarizing here on the periodic table, the vertical groups have similar chemical properties. Horizontal, not so much, but that periodic law deals with those rows, those vertical rows. Vertical, I guess that's columns. But the periodic table is arranged to group those. Now we're going to see here in a bit how it got arranged like so, why it's got looks like a bunch of stuff is missing and there's only 2 things on the top row. There is a reason for all that. Oops. All right, so the reason is this guy right here, Wicked Beard here. 1800s, Mendeleev actually proposes this as a periodic table. And you notice this looks nothing like the one I'm giving you in the class. But the reason Mendeleev's periodic table took off and gained some traction is because at the time he's doing this, elements are being discovered a lot, being purified and analyzed and turned into proof that they are atoms. So everybody who's making a periodic table has to redo it every 2 or 3 years because more elements get discovered. Well, Mendeleev started leaving holes. Like if you look right here, see how that just has a dash before this number 72? Well, he knew something below carbon, silicon, and tin. There's a reason these are shifting back and forth. But if I'm going to, carbon was everything, and then silicon, tin, and anything that was like right shifted on his table is supposed to be in the same group. So it's weird how it's set up. But he knew that there's supposed to be something between silicon and tin on his periodic table. And he just left a space for it and said, well, I know it's going to weigh 72. Matter of fact, he made a bunch of calls on it. He said, this thing that's supposed to be under silicon should have an atomic mass of 72. It should have a density. It should have this color. It should have a density of its oxide of this. Should have a boiling point of its chloride. So ecosilicon chloride. So he made all these predictions. And when germanium was finally discovered, it was found to fit these perfectly. Now, the reason that is because if you look back to our periodic table, it's done. There's your carbon, there's your silicon, there's your tin. Germanium is in that column. And that column tells us similar chemical properties. So since he knew things about silicon and he knew things about tin, he technically knew things about germanium. All right, but by the end of his life, his periodic table looks a lot more like ours. A lot more empty spaces because it wasn't until the 1900s that most of those hollowed out numbers on the periodic table got filled in, 1920s at the earliest. It was something that took off and is accepted. That's why he's considered the father of the periodic table. All right, so periodic table is going to be arranged in those groups, those vertical columns, telling us the chemical properties, and periods are going across. Now, periods really are just telling us about roughly the amount of energy in an electron or in an atom. They're not necessarily telling us anything about the chemical properties. All right, but that's all of them. We have our blue ones here are our metals, yellow ones are nonmetals, green ones can be either or, they're called metalloids. And then the white ones, we're not sure. That really has a lot to do with the fact that there's not many of them in existence, and all of them, once they were created, basically self-destructed almost immediately. So they're likely all metals, even this one over here, even though it's in that noble gases row, it's probably going to be considered a metal when it's actually finally studied. And that has a lot more to do with the physics of what's going on in the nucleus than the chemistry. All right. Now, my periodic table doesn't actually single out solids, liquid, and gases, but the only two that are liquids is mercury, which is right there in the periodic table. Mercury you find in thermometers sometimes, not so much anymore. And the other one that's a liquid at room temperature is bromine. All right, bromine, for instance, the liquid's down here at the bottom. It actually vaporizes quite easily, which is what this brown gas is. That's bromine vapor. But the brown liquid on the bottom is actually liquid bromine. All right, so our metals, nonmetals, and metalloids have all those unique properties that you would expect from metal. Most metals conduct electricity, have a luster, they're malleable. Even I mentioned that my sodium, if I were to go to my chemistry lab, is covered in like a white powder. If you were to clean that off and like cut it with cut the metal open, the inside of the metal would still look like metal. It reacts very quickly to the air and would actually corrode up. Nonmetals don't. They typically do not conduct electricity, and they're not really malleable. They're powders in many cases. Like sulfur is a yellow powder. Metalloids can be a mix. And what I mean by that, they can have metallic-like properties and non-metal-like properties. But as we understand our metalloids more, we've been able to manipulate them. Like if you think about your computer chips, silicon chips, there is a reason that's used, because they can start with that silicon wafer and they can draw on parts of it to make it conduct electricity, make it behave more like a metal, and draw on other parts and make it not conduct electricity. So they're actually drawing the electrical circuits by just changing the conductivity of the silicon. Okay, our groups that we give names to, I already mentioned the noble gases. And we talked about group 1. Those are the ones that react very violently with water. We actually call them alkali metals. And then right next to that, alkaline earth metals. And then halogens are just pretty gases. They're very colorful. That's why they get their special name. So halogens here, group 17, noble gases, group 18. Alkali metals, group 1, and alkaline earth metals, group 2. Now, almost everything else does have its own special name. We call these transition metals, and these get named after the first elements. But those 4 I covered on the slide are the most critical for us to know right now. We're going to be talking about these a lot more, and those of you who go into Chem 2, or General Chemistry 1 and General Chemistry 2 are going to get a lot more of these. But they're just metals that have different reactivities than group 1 and 2. Right, and there's our colorful bromine and iodine. Chlorine's actually kind of a yellow gas. Okay, so we want to actually classify this first group as a metal, nonmetal, or metalloid. And all we need to do is look at our periodic table. So that first one does say iodine, and we just find iodine on our periodic table. It's right there. It's yellow, so we actually can truly say that's a nonmetal. Piece of cake. You just find it on the periodic table and tell you what color it is based on those colors. We're not going to bother to do the other two, but they are metals. I'll just answer them rather than go back and forth. Now the next one's a bit of a trick. So group 14, period 2. So the reason I say it's a trick, I can find group 14 easy enough. Period 2, you might say 1, 2, and say silicon. Well, the weird thing is the periods are by the row. So there's Over here, this is period 1, this is period 2, 3, 4, 5, 6, 7. And this is part of period 6, and this is part of period 7. So group 14, period 2 is actually carbon. There is no period 2, or there is nothing in group 14, period 1, but there is in period 2. So that is actually carbon. And then the noble gas in period 1, so top row, noble gas, that would be helium. Okay, the natural state of our elements is mostly a mixture. We don't actually find too many elements all by themselves, as in pure elements. Now, the exceptions are the noble gases. Helium, neon, argon, krypton, xenon, radon are typically never found as part of chemical compounds. And in our metals, the only ones we typically find pure too often is gold, silver, and platinum. And even gold we typically don't, because the purer the gold is, the more malleable it is. So it bends easy. So we actually typically use alloys of gold just to make it harder. And that's really how we find most metals. We make alloys to give them very particular strengths. Like in your car, there's a lot of iron, but the other elements added to the iron give the metal different properties. Side impact beams, for instance, don't bend nearly as well as the car itself because they don't want them to bend. Because if they bend, they don't work as side impact beams. All right, the diatomic molecules are where we find a lot of our nonmetals, and it's about the closest way we find them to pure. So the oxygen in the atmosphere is O2, but it's not really safe to say the air around us is pure because also in there is nitrogen, N2. And here in Florida, there's going to be some water vapor, there's going to be some carbon dioxide, there's going to be plenty of other things, but the majority of our air is oxygen and nitrogen. But all of these come up as diatomic molecules and can be found pure, but typically are found as mixtures and other things. Okay. Excuse me. Regarding our atoms and how well they conduct electricity, for the most part, metals conduct electricity, nonmetals don't. There are exceptions on both, and there are metals that conduct better than others, and there are nonmetals that do conduct. Carbon, for instance, can be found as diamonds and as graphite. Turns out graphite will conduct electricity. But for the most part, nonmetals and compounds made of nonmetals are less conductive electricity. Water is a good example of that. Turns out water is a very poor conductor of electricity. I got this picture in the next slide. If we were to actually take some pure water, put some electrodes down in there and try to run electrical current through it, nothing will happen. Which is really weird because if you think about hair dryers and almost any electrical appliance tells you not to use in the shower, this would seem to say, well, the water is pure, I should be able to use that and it not electrocute it. Well, problem is, our water we use on a day-to-day basis is not pure. We always have small amounts of electrolytes in there. Now, electrolytes can be simply salt, and it might not be enough for you to notice it's there, but if you were to go to Walmart or Publix and buy some distilled water and drink it, you would notice a drastically different taste. And that's because all the water we come in contact with on a day-to-day basis has some of these electrolytes in it. Matter of fact, here's a weird one. All right, so let's unhook this battery, and let's just put our hand down in here. So I've unhooked it so there's no way it can shock us. But we're going to leave our hand down in there for a few minutes. And then pull our hand out and then connect up the electricity. Even if we freshly washed our hand, there are enough electrolytes in the cells and the skin cells and on the surface of our skin that we would probably have transferred enough electrolytes in there that this light would come on. Doesn't take much, dissolves in water very easily. But gosh, this would probably turn on if we were to go grab a little salt thing from like a Walmart, from a McDonald's or Wendy's, and if we emptied that salt container in there, that'd be enough to get that electricity come on. It doesn't take a lot of salt ions to fully get those electrolytes up. Okay, electrolytes are ions. Now, most of our ions are actually just going to be split into two groups. Actually, all of them are split into two groups, cations and anions, and that really comes from the charge. A positively charged ion is a cation, negatively charged ion is an anion. They get these charges because we lose or gain electrons. Remember when we talked about with our periodic table and we said that the number of protons and electrons were the same? When ions, they're not. And an ion, you gain electrons or lose electrons to actually change that charge. What I mean by that, let's think about sodium. It's one of our group 1 atoms. It's on the third period down. It actually has an atomic number of 11. So therefore, in a neutral one, it has 11 electrons. Well, if I get that sodium to give up 1 electron to become just 10 electrons, it becomes a positive charge. And calcium could do that for a positive 2 charge. Matter of fact, on a periodic table, we can safely say everything in this group 1 can give up 1 electron and become a positive 1. And everything in group 2 can give up 2 to become positive 1s. Now, the reason they're giving up electrons, if I were to look at sodium and go back to 10, it actually is going to start to behave a little bit more like neon. More importantly, its electron cloud is going to behave like neon. An electron cloud is what helps that reactivity. Sodium ion is slightly less dangerous. It's not reactive. Matter of fact, it can float around with water without any problem whatsoever. Unlike sodium solid or sodium metal, if that comes in contact with water, it very rapidly reacts with water. But sodium ion does not, because those electrons have been changed. So we do find that everything here in group 1 and everything in group 2 gives up 1 or 2 electrons. Sodium will always turn into a positive 1 ion. Calcium will always turn into a positive 2 ion. Now, technically, these ones in the middle we're going to skip until you get to intro chemistry. The only other one we're really going to do anything much with is aluminum right here. Now, it's in group 13, but if we count back 1, 2, 3 spaces, we'll see that aluminum likes to form a positive 3 ion. And I'm actually going to put that right here below this. So aluminum, which actually has, 13 electrons, will actually become Al3 plus with only 10 electrons. Same number of electrons as our sodium ion. Now, when we actually have an ion, that's all we do to name it is actually put the word ion after it. So that Al plus 3 that we just put up there, we really do just call that aluminum ion if we were to name it. Aluminum ion is just Al3 plus. All right. Our anions, the exact opposite. Anions, you're going to gain electrons. Now, the number of electrons they gain can be actually deduced from the periodic table as well. Like what I mean by that, everything kind of like the metals want to become like they want to become like a noble gas. The non-metals do too. So fluorine, if it gained 1 electron, would be just like neon. Oxygen would want to gain 2. Nitrogen would want to gain 3. And carbon, if it does it, wants to gain 4. Well, that just tells us the charge. Everything here in group 17 likes to be a negative 1 ion. Everything in group 16 likes to be a negative 2. Everything in group 15 likes to be a negative 3. And you can make that call every single time. That's just how it's going to be. So I'm going to put down here the nitride ion of N3 minus. Now, unlike the cations, when we name an anion, we're going to change the suffix on the nonmetal. It's not fluorine or oxygen or nitrogen. It's fluoride, oxide, nitride. You change the suffix every single time to IDE, and then you say the word ion. All right. So when we put these together, what we're going to do is take an anion and a cation. It's going to be mostly that metal and the nonmetal as an ion. And we're going to combine them so that the electron charges balance out. What I mean by that, we're going to come down here. So we have calcium and bromine, right? Now I'm going to look at the periodic table, and we see that calcium being in group 2 would want to be a +2 ion. Bromine is one of our halogens in group 17, so it'd want to be a -1 ion. Now, when I go to combine these, I want those charges to cancel out, so I'm going to increase the number of bromines so that the amount of negatives is equal to the amount of positives to give us that the formula for this would be CaBr2. All right, this aluminum right next to it, we get a +3 for aluminum and a -2 for oxygen. To get these to cancel out, the common factor between these two values would be 6. So I'm going to get 2 aluminums for every 3 oxygens. There are some people that have been taught reverse those numbers, which definitely works. Put the 3 with the oxygen, put the 2 with aluminum. Can't do that here. Don't want to use those numbers with magnesium sulfide because these are both 2s. Magnesium sulfide is just MgS. Now, that's how we do the formulas. To name them, we just use those names that we used in the anions and cations. We just drop the ion part. So it's not calcium ion and bromide ion. It's calcium bromide. We put them together. This would become aluminum oxide, magnesium sulfide. Just put them together. All right, so what do we get here with calcium and nitrogen? Our strategy is always the same. Look on the periodic table to get the charge. That is 2 positive. This is 3 minus. And we're essentially going to reverse those. So we're going to need 3 calcium for every 2 nitrogens. And that gets us ready for this, gets us finished up with